No, not yet.
It's
okay.
better.
Yes, much better. Okay, let's begin.
So I think that my talk will be extremely elementary on the school level, I think. So the main talk is just, main goal of this talk is just to explain what is quotient of differential equations and what we will get in the result. So I will begin first with some negative information about quotients, and then we'll move to the positive side and we will explain what happens with differential equations if we will factorize them or take quotients with respect to the symmetry group. So let's begin with the first very elementary example. Let's take group, the text on some set. Then the quotient is a set of all orbits. And what I wanted to stress here that if, like we do in geometry, we'll try to explain our objects in terms of functions on them, then the quotient functions on the quotient is just exactly G invariant functions. So the last line is just a condition that function doesn't change under action of our group. Okay, so less elementary. It's what happens if you will take topological group, topological space, and make the same factorization, take quotient. Then it's also well known that the quotient will also topological space, but there is one but very important remark that if you begin with some sense nice topological space, the quotient can be extremely ugly. I just will give you two examples. I will use it later on in our situations. So example number one, it just takes the plane R2, take all linear transformations in GF2, natural action, and take quotient. You will get 2 points. One is orbit of 0, and the second orbit of any non-zero point. So the quotient of this topological space, it's very nice space, by the way, manifold, algebraic manifold, smooth manifold, analytical manifold, and group also very nice, V group, algebraic group, and so on. But the quotient is extremely ugly, because if you analyze topology of this quotient, you will see that 0 is a closed point, and star is the open point. And this is a very strange topological construction. It's known in general topology. It's called Sierpinski topology. And what we can say about this space, it's topological space, but I'm a little skeptical if it takes so nice objects and factorize and get so ugly topological space, what we can expect in more complicated situations. And the second example, it's the same R2, action of multiplicative group of non-zero reals, and the natural multiplication, scaling. Once more, when you take quotient, you will get 2 pieces. One piece is the same, this is fat 0 point, or not fat, that's in orbital 0 point. And the second, it's very nice object. We like it very much. It's projective line. So in some sense, if you will remove this is 0, then the quotient will be once more. If you work with the manifold, the quotient will be also manifold. So the question what you should remove to get something nice. Say in the above problem, what we should remove, 0 or star? What will be the nice object for us? Okay, so this is what happens with topological spaces, and let's make next step. Take smooth manifolds, and honestly, I know only this is the last sentence, that if it will take quotients of manifolds by free actions, and proper, then we will get once more smooth manifolds. It's a source of very popular in geometry G bundles. But in applications, especially applications to differential equations, what I want to do, it's very rare we will get free and proper actions. And that's all that at least I know about quotients. Everybody knows about, say, irrational winding theory, where the quotient will be so ugly that it's very difficult to imagine how ugly it is. Okay, now the first nice news, or good news in this story. It's so-called Rosen-Lychagin theorem. I just give some biographical remark about Rosen-Lychagin. For me, it also was a surprise that he lived up to 1999, so practically to our time. So yeah, and also one point, it's that he was student of Oscar Zaritsky. Zaritsky, as I remember, he came from Kiev, so it's Ukrainian trace in our talk. So what is the theorem about? Yeah, this is, I found on internet his photo. So this is Rosen-Lychagin. Yeah, and so the Rosen-Lychagin theorem, I just will not formulate theorem as a theorem, I simply will explain what's really going on here. So first of all, we will start with algebraic manifold. It's just when you define, say, smooth manifold, you define by Chats and require that this is transition functions between the Chats should be simply diffeomorphisms. And if you will require that this is transformations given by rational functions, then what you will get is called algebraic manifold. It's just a very special case of so-called algebraic varieties. So it's, sometimes they call this varieties without singularities. Okay, so this capital omega, this is algebraic manifold, G algebraic group. So it also means that it's algebraic manifold together with operation that should be, say, in coordinates should be written with some rational functions. And there is there is some action of this group on our manifold. Once more, it's algebraic action means that formula for these transformations will be given by rational functions. Okay, yeah, f omega, it will be rational functions on this. And the standard f omega in degree g, it's field of rational G invariants. Now, it's not exactly what Rosen-Lychagin proposed, but it's what we get from simply from experiment. So when people say that some orbit is regular, very often there is no common opinion about what means regular, what means non-regular. So sometimes it should be saying that it should be maximum dimension. Sometimes it should be closed. So and so on. So if you want, say, to have something like the quotient should be like Hausdorff space, then certainly it should take closed orbits. But what we want to have in as a quotient something that will be very similar or will look like our omega. So the omega was algebraic manifold. So the main property for this, it was that we can find some Chats and rational transformations within them. So let's put in our definition regularity as a condition that quotient will be in some sense some point where our quotient regular orbit will be such orbit that in quotient it will be a point where our quotient is a smooth. Another way that it should be point such that we can find some local coordinates at this point. In terms of our capital omega, it says that, okay, functions on factor is just invariants, and conditions that this is, say, some number of invariants will be coordinates at point g omega, it simply means that the differential should be linear independent, at least at the point of our order. So now let's take omega 0, it's a set of all regular points. Yeah, so we just remove everything that is not regular. And then this q omega, it will be our standard quotient, so it's a set of orbits. Then, first of all, it's clear that we just, with decision regularity, we put it conditions that this is rational functions, rational invariants will be like local coordinates on this quotient. And the transformation between two such coordinates obviously will be given by rational functions, so it will be just algebraic manifold. And so the main, it's easy to say, but we don't know how big this omega 0, the set of regular points. It can be, say, empty, and then all the results will be just complete, just without any sense. Once more, Tor and irrational winding. But this is the main part of, or main point in Rosen's theorem. He states that this omega 0 is open is more or less obvious, and the more important it is dense. So it means that we can remove some number of bad or singular points from our manifold, and the quotient will be just once more algebraic manifold. So what else we can add here? It's, oops, sorry, it's the last. I'm sorry for my typing. The last line, where it states that simply rational invariance of this action, it will be image of all rational functions on the quotient. It's what really we expect in taking of quotients. Okay, so this is I would, this for me, this is the more valuable result in theory of invariance. Okay, and now just comments to this. So really, if you just will analyze what I said, it's not important that we have algebraic manifold. We can take say smooth manifold, really not always smooth, but say smooth manifold. Then we can repeat it, our definition of regularity by a requirement that there are necessary number of invariants that will serve as a local coordinates in the quotient. And then quotient will be once more say smooth manifold, blah, blah, blah. But the only point, and this is the main point, that this is omega regular, the set of regular points, can be just empty. And so there is you can repeat it construction of Rosen's theorem, but in Rosen's case, it says that we can remove very teeny subset from omega, and the result will have very nice quotient as a projective manifold. Okay. Now let's approach to differential equations. Really, it's very rare when we computed symmetry of differential equations, we knew the symmetries as transformations. Yeah, certainly there are some equations where say all diffeomorphisms are symmetries. Then we know them certainly as transformations. On practice, when you computed symmetries of some differential equations, you will find Lie algebra. And now the question, what we can we use any Lie algebra and apply this as Rosen theorem or not any? So first of all, let's introduce such notion, algebraic Lie algebra. So it should be Lie algebra that so we take some Lie algebra vector fields from our algebraic manifold, and so algebraic Lie algebra is simply an algebra that corresponds to some action of algebraic group on this manifold. And if it's not so, then we have algebraic closure of this algebra by saying that it intersection of all algebraic Lie algebra that contains this our sub-algebra. So the strange notion, but really we'll need it. So just few trivial examples. So example number one, it's a favorite SL2 algebra on the line. It's GDEq, X GDEq, X square GDEq. So it's obviously algebraic action because it corresponds to projective action of SL2 on the line, on the projective line. Really. And the second example, this is I mentioned a few times, is the torus. So if you take, say, torus as a product of two circles, then such vector field dphi plus lambda dpc, if lambda is not rational, then you know that orbits or trajectories will be dense on toric. So we have no here any non-trivial invariants or integrals of this, or first integrals of these vector fields. And the same for R2, if you take also very trivial, I'm sorry. Okay, the second part, it's another, okay. Just let's talk about toric. So the second one is not true. But if you take this irrational widening on the toric, then the smallest algebraic algebra that will contain this vector field dphi plus lambda dpc, it will be just algebra dphi generated by these two commutative algebra generated by two vectors dphi and dpc. Okay, now when we can apply this Rosenlich's theorem for Lie algebra actions. So it's obviously we should move from Lie algebras to the corresponding group. And if you have algebraic group, then algebraic Lie algebra, then we have this algebraic group that stands behind all this algebra. And then the algebraic invariant, rational invariants of our group or rational invariants of our algebra will be the same fields. But if our algebra is not algebraic, then we should take closure of this algebra and then take invariance of so rational equation, rational invariance with respect to G. It's the same that rational invariance with respect to the G tilde. And by the way, also dimension of this field, it will be also co-dimension of G tilde orbits, but not G. Okay, it's the only remark that I wanted to add here. And now let's go to equations in two jets. First, I will remind some elementary but important properties, not properties, facts from jet geometry. It's they simply show that in some sense algebraicity it's just very natural ingredient in differential equations. So so GK, it will be just k jets of say some bundle. And what we know about geometry on these spaces, it's that there are two pseudo groups that stands behind the geometry. The first is if the dimension our bundle P equal 1, it's contact transformations of one jet space. And if dimension bigger than 2, it's all a diffeomorphism of G0. And this is just so-called point transformations. So this is the two groups that control geometry of jet spaces. So what we know about these groups? First of all, it's also important. There are some defined structure on bundle. If you take projections in k bundles, k-1 bundle, then this is bundles themselves. They are affine bundles if you take k bigger than 1, if dimension more 2 or more, and k should be bigger than 2 if dimension equal 1. And it's a fine structure, but also what we know, at least if we computed prolongations of, say, point transformations or contact transformations in jets, you will see that all this is lifting of prolongations will be just given by rational functions. Very special, but rational functions. So it means that this is fibers of projections, say, from k jets, fibers of projection from k jets to 0 jets. In case of point transformation, they are algebraic manifolds, and the same projections from k jets to 1 jets. It's also algebraic manifolds for with respect to contact transformations. So if you make contact transformations, it will be some birational transformations on this on the fibers. Yes. Yeah. Okay. And now also funny notion algebraic differential equation. We had algebraic Lie algebra, now algebraic differential equation. So algebraic differential equation is equation, so submanifold in k jets, such that the intersections with the fibers to 0 jets are algebraic submanifolds of fibers from gk to g0. And this is conditions to be algebraic. It's important. It's invariant conditions. It will be not changed if you just make some point transformations. The same for dimension for bundle of dimension 1. If you take projections from from this equation to 1 jets, then if this projection is algebraic, if this intersection of gk with the fiber of this projection is algebraic submanifold, then it's invariant under all contact transformations. So the notion of algebraicity, for roughly speaking, for systems, it's good for all. So it should be equations that should be algebraic in first jets, in first derivatives and second derivatives and so on, but it can be arbitrary in on the level of 0 jets. And the same for one-dimensional case where equations assumed to be algebraic in second, third, and so on derivatives. And this is condition is just invariance. It will be not change it if you just will make some transformations over them. Okay. Yeah, and so if, yeah, certainly I will talk only about formal integrable equations, so I will not say it time to time. So, but if the case, if it's formal integrable, then if you take this prolongations, it's once more you will get algebraic equation. So it's starting from level k, all other higher levels, k plus n, will be also algebraic equations. Okay, this is first why I'm interested in algebraic manifolds in this type of algebra. So really, when we work with differential equations, this algebraicity is equations. It's really important. It will be important for us. Okay. Now about symmetries. So for systems, symmetries usually for us will be just not usually, but practically every time it will be point vector fields. And if we take symmetry as a group, then it will be a subgroup of point transformations that preserve our equation. Then preserving of our equation, if equation algebraic, it's look like some algebraic equation for our transformation for group elements. And so we expect that groups will be algebraic itself. But when we talk about Lie algebras of symmetries, then first of all, we never know, do we know all symmetries or we know only part of them? So the whole algebra of symmetries will be algebraic, but subalgebra will be not. Maybe not, maybe yes. Strictly speaking, you should check it. But one recipe how to see that everything okay, it's first if you will compute the invariants and they will be rational functions. It's important for us, and if you have codimensions and independent invariants have the same dimensions, then it's just show you that possibly you work with the algebraic algebra. But you can check it directly that you have some algebra, you can check it directly that it's algebraic or not. Okay. Now let's go to quotients. So we will see that we will say that symmetry. We will assume that symmetry algebraic every time for us. And moreover, we will. Okay, let me talk only about finite dimensional case, and it's not important to say how big this algebra G. It can be also done for infinite dimensional, but I will simplify my life. So let it will be G algebraic Lie algebra, and it's X on our equation K and all prolongations of K. So this is algebraic, and as we see, all this is our equations of fibrous equations, EK, EL, and etc. They are
something wrong with
what?
Yes, now it's okay. Something wrong was
no, it's I forgot to say the more important stuff. So we'll assume that our symmetry algebra is that, say, for point transformation, it should be transitive on G0. And for contact, it should be transitive on 1Gs. It's why we need this, that practically every time I will talk not about group itself, but about stationary subgroup or stationary subalgebra, stationary of point of G0 or G1. Is the one because this fibrous will be algebraic, and fibrous at this point will be algebraic submanifolds, and the groups that will act on this fibrous, it will be group of our stationary group or our stationary algebra. So requirements to be algebraic, I'm sorry, I should correct myself. So algebraicity means algebraicity of this stationary subalgebra or stationary subgroup. Then this is G will act on all this submanifolds, all these manifolds EK and EL, and because it's algebraic, Lie algebra algebraic group, if you wish, then we can make quotients of each of this level. So we take on each levels in on level GK or level GX, it says we take all regular points for this our G action, but I will a little change the notion of regularity. So regularity will be regularity in our whole sense plus one more point. The projection of this point on the previous level should be regular too. And then we will get quotients on each level. L, we will have this quotients QL of E of our equation, and all of them will be just algebraic manifolds, as we saw from in Rosenlich's theorem. So yeah, and functions on these quotients is just exactly a rational invariance, rational differential invariance of order A. Really, we have more than this. So we have not only this projective manifolds, we also have some distribution of this. So if you take the Cartan distribution from our equation and push it on our quotient, we'll get, because our group preserve Cartan distributions, then we will get some distributions on these quotients. So practically what we will get this sequence of algebraic manifolds together with projections. It does matter, final net, and plus some image of Cartan distribution on this ones. So it's look like case when we have equations. The only that now it's not jets of something. It's just some simple projective algebraic manifolds and rational maps between them. How to see this in more visible terms? I will remind you this notion of three-set derivatives. So the first is some operations of taking horizontal part of differential forms on kz. So if you take some, I like omega, so now omega is differential one form, but not point. We take this form, just lift it on k plus 1 jets, and consider this modular annulator of Cartan distributions on k plus 1 jets. So we'll get some not differential form, but some class on k plus 1 jets. And we remind that we start with a level of k jets. So let's call this horizontal part of omega. So if you take the standard coordinate, jet coordinates, then it's look like this. So this is our differential one form, and now this is horizontal paths. So it's look like this. So we should, instead of this differential of this u sigmas, express them just as a Cartan form plus this term. So so first of all, this is why I wanted to talk about this. This construction to take in horizontal path is invariant. So if I make contact transformation or point transformations, this form will behave in a natural way. So I will use this construction for functions. So I will take function and take differential of this function, take horizontal path. And this is what I will get. It's called the total differential of our function. And in coordinates, it's look like this. It's like standard differential, but instead of partial derivatives, we take here total derivatives. And these constructions allow me to make some to introduce some important operation over invariance. So let's take some number of functions on kjets, n functions, and n is exactly the dimension of our base of our bundle pi. And we'll say that this function independent if their total differentials will be linear independent. So this means that this product not equal 0. And certainly some domain, not everywhere. So if you take in this domain some function and take total differential of this function, it's can be represented as linear combinations of total differential of these functions f1, fn. This coefficient that we'll get, this is they call Tresset derivatives. I will use this notation for them. This is df dfi. Why all of this? So assume that we have invariants now with f1, fn, and some g invariants. And let's f also will be g invariant. So if I will make this combination, this is fy. So as we saw, this construction of total differential, it's just invariant under transformation. So it will be also g invariant. And the right-hand side also g invariant. This is the composition is unique. This fj's is also unique function. So they also should be g invariant. And so what we see that from this data f and f small fi's, we'll get this capital fi's, and they are also invariants. One remark, all these functions f1, fn, and f itself, we took on the level of kj's. And this construction, if you will check it, it says that this fj in general should be a function on k+1 j. But it will be invariant. So it means that this construction, taking these derivatives, allow us to get, in general, to get invariance of order k+1 if you know n independent and one more invariance of order k. So, and this is a big difference between algebraic theory of invariance and differential theory of invariance. In algebraic theory, we take only this elementary algebraic operations of invariance, and they did not extend the set of invariants. But now these Tresset derivatives, they will give us really new invariants after derivations. So this is what I just said. Now, just also some biographies, information about Tresset. It's Arthur Tresset. It's he finished this École Normale Supérieure. It's in 1891, and he did it together with his friend. It's Elie Cartan. After this, he was student of Sophus Lee in Leipzig University, and his thesis, and also it was after the book, it's called invariance, differential invariance of continuous group transformations. I also found one book more, really very teeny information about him. Just I did not find his photo. Only 2 or 3 publications. Okay, but I didn't know that he was really a student of Lee and that he studied together with Cartan. Also, he in Leipzig, he met Wilhelm Killing, and after this he came back to Paris and presented to Cartan works of Killing, and this was origin of work activity and Lie algebras. And by the way, and the notion of Lie groups, it also belongs to Tresset. He introduced this notion in his thesis. Lie was his supervisor, so this was very natural. Okay, so this is Tresset. And now, theorem that I wanted to say, it's so it says that okay, local variant, but local variant it sounds a little silly, but anyway, it's people believe and think that it's goes to Lie and Tresset, but local version it's not what we really need. And okay, from my point of view, certainly, Borja Kruglikov and myself, so we published in Selecta in 2016 this paper with the name Global Elite 3C Theorem. And what it says the following. So if you take algebraic formal integrable differential equation and Lie algebraic symmetry Lie algebra. So this means, to be precise, it means that this algebra acts in transitive way on the level of 0 jets on 1 jets, and the stabilizer of this algebra at points of 0 jets or 1 jets, depending on dimensions, they should be algebraic. So they should give us algebraic actions on this GK. And so in this setting, there are rational differential invariants. You can find rational differential invariants and n is the dimension of our base, and n capital, it really depends. So you cannot fix this n capital. But anyways, such number of invariants, such that all other invariants will be just rational functions of in this A, B's and in 3C derivatives. So in some sense, if you're lucky enough and you find this is n capital plus n invariant rational, then you practically found everything. So all other invariants will be just algebraic rational functions of this, and this is 3C derivatives. Okay. Now just I approach to what I wanted to say about quotients. So when you have this as invariants, they generate all other invariants by taking rational functions, but only generate. So possibly there are some relations between them. So, but relations between them will involve these functions and also these 3C derivatives. So it means that our syzygies will look like differential equations. So this is differential equations in what we will call quotients equations. And this is really means that this is tau that we constructed when we took quotients of our equations by action of our group. So really this quotient, this tau looks like infinity prolonged equation. So we take this CDG equation and take prolongations of this. At least it's locally, so it does mean that it's represented this A's and B's just global coordinates. They are just local coordinates, and so it means that we represented this tower as a at least locally as some infinitely prolonged differential equation, and this is just follow our seminar. It should be called Differential, but because it's two such differential equations related to each other, rational differential transformation. So it means that it's rational transformations that involve not only our functions A and B, but also their derivatives. So it means that I will, let's call this algebraic differential, in the sense that when we take algebraic manifold, is different from smooth manifold by assumptions that transformations should be rational. So here also transformations will be rational. Okay, now few remarks about relations between our original equations and the quotients. So the first, it's just how to construct quotient equation if you know equation of quotient equation, if you know solution of original equation. So we take this, say, u equal fx as this solution of your differential equation. And then if you take our invariants ai's and bj's, they take their values on this section of function f. So this, by assumption, in general situations, they can be sorted as a local coordinates, and this can be expressed then as a functions of these ai's. So we'll get this relation. So if you remove now this f and simply write this bg equal fga, then this will be solution of the quotient equation. It's analytical manipulation, but geometrically saying that you take solution of your equations E, and now take orbit of this solution with respect to your action of your group G. And this is orbit, it will be solution of our quotient equation. So it means that if you take solution of quotient equation, it means that you know orbit of some solution of your equation. The only we should be careful when we talk about solutions, because the only what we know that passing from equation to quotient to projection, it preserves Cartan distribution. It doesn't care about is it smooth section or a smooth section. So solutions we should understand as an integral manifolds of the Cartan distribution. Then it will be okay. Now, yeah, and one remark more. So if you have a solution to the quotient equation, what we can do with the solutions of our original equation? So it's related to so-called differential constraints. So if you have differential equations, very, I would say smart, but not so smart, but one of the desire just to add one more equations and one more, and maybe finally you will get a solution. It's certainly if you think the solution of equation some submanifold in our manifold E, so to specify this equation, we should add more and more condition of this equation. On this equation. But it's very dangerous to add, if you have a system of differential equation, it's very dangerous to add a single equation more. So with probability 100%, you will get some very silly result. It will be equation without solution. So in our case, if you take this relation, so BJ is equal or minus a BJ, this relation on differential invariance, you can think that some relations on jets, and you will add these relations to our equation E. And then what you will see that it will be compatible constraints, and you will get really new equation, and this is equation will be just exactly orbit of some integral manifold on E. In other words, when you will do this, you will kill all characteristics, and when you add this relation to this, you will get and restrict Cartan distribution on this. You will get completely integrable distribution on your on equation and integral manifold. So this will be just solutions of our equation E. And one also funny remark that if you take symmetry of quotient equations, so as we saw, solutions of quotient equations are just orbits of our solutions of our original equation. So quotient, it means that you will move orbits to orbits. In other words, if I take solution of my original equation, take orbit, apply symmetry of the quotient equation, I will get new orbit, but not new solution. So it's a way of, it's a way to get some family of solutions from one solution. I don't understand what it is. Okay, now just very short, just few. I'm sorry, what it is?
Can you do Control-Z or something like this? So to remove the last action. Control-Z.
Strange. Okay, I'm sorry for this. I don't know what it is. Okay, so just a few examples of constructions of quotients. So I will start with the ordered differential equations. Its computation is much simpler and much visible. So let's start with the group G. It's just translation GDEq. And so just without any equation. So what is the differential invariance of this group? So it's easy to understand that it's in jet coordinates, it's our function of derivatives. And let's take, this is A and B of this in Lychagin theorem. So let's take A to be, this is Q0, it's the first Q, and B as a coordinates, and B as a function is Q1. So then this operation of taking three derivatives, it's very simple. So this operator. And if you apply, say, I will use this notations B1 and B2 and so on, it simply means that it's first derivative, three-set derivative of B and the second derivative. So this is the first derivative of B, this is the second derivative, etc. And if you just will take equation of third order, this F, and remove this U's and substitute by B's, you will get this equation of the second order in this interset derivatives. So in some sense, this is the way of getting from equation of third order, equation of the second order. It's we studied this trick at school when we learned how to reduce order of our equation if our equation doesn't contain x, contains only derivative. I don't understand what's going on the picture.
Там резинка есть, можно вытереть резинкой все это. Сверху в опциях.
Где, в каком месте будет резинка?
Ну, сверху, если подвести мышкой, там будет это самое, ручки всякие, резинки.
Да нет, у меня почему-то они сами по себе возникают, эти картинки. Я не понимаю.
Ну, ты планшетом пользуешься и рисуешь на нем.
Нет, это не планшет, это компьютер.
Да? Ну тогда, значит...
Это какой-то участник у вас пишет.
Да, на самом деле это может кто-то другой пишет. Is it possible that somebody actually writes on his screen?
I don't know.
This is strange.
Не думаю, не может шерить два человека.
It was in our conference with Rafael, it was like this, somebody wrote on the screen.
I would guess it's someone from the outside that are not part of this conference.
Okay. Anyway, I will sorry. And the second case, I will take the same group and the same jets, but I will change a little choice of this coordinate A, and instead of U0, I will take U2. Then, if you check it, how three-set derivatives look like, so it will be just, you see, it will have this multiply third derivative minus 1, and if you now you have two b's, and it's more or less clear that if you take only one b, you say if you take u0 to be only one b, the second is component u1, you will never get it by derivatives. So because three-set derivatives immediately give third order function. So you have to choose two b's here, and the simplest way is to take, say, u0 and u1 to be, this is b coordinates. This very easy computations of derivatives. first derivatives of B1 and first derivatives of B2. So if you just will check it without any equations, you will see that should be some relations between derivatives B1 and B2. And so this is the last line. It's first derivative of B1 multiply on A, it's equal square of B multiply on square of first derivative of B. So, and it means that if you take our third order differential equation as before, then the quotient will be the system of two equations. So, but it's what I said that if you just check one A's and B's, and you will get one differential equations. If you take another A and B's, you will get another differential equations. Maybe in the first case it's also just one equation. In the second case, you see, is the second equation. And transformation, there is transformation that certainly we can easily express this first A and B's in second A and B's just by using these formulas. So, and relations between them will be just, they will be expressed by rational differential expressions. So it's correspondence between Alexander. We have SPI. Opa. Okay, so and one more construction. If you just take affine group, so just GDEq and XGDEq, then invariance, it's this line. This is how invariance look like. It's also more or less obvious. And once more, if you take A to be U0 and B, this is this is next invariant, U2 divided by U1 square, then you can easily find this is derivatives B1, B2. And what happens that if you take this G invariant equation, so like functions of U, U2 divided by U1 square, and so on, this up, I wrote up to the order 4, then the quotient will be equation of order 2. And this is for funny phenomena. Then if you have, say, now dimension of our group equal 2, and from equation of order 4, quotient have order 2. So we reduce it to 2 degrees. So 2 orders. And it happens every time. So if you take equations, say group of dimension L and equation of order K, then passing to quotient will be reduced order on L.
I'm sorry. It seems that well, we have 2 copies of Sasha Aksionov here, and one is original Sasha, and the second one is some hooligan who interferes with our seminar.
So what? How he doing?
Yes, because
Иосиф Семенович, у меня все в порядке. Сейчас. Иосиф Семенович, у меня все в порядке, у меня на экране хулиганство полное, но мы ничего не делаем.
Я понимаю, что вы ничего не делаете. Значит, там просто вторая копия ваша появилась. Это не вы, а кто-то влез.
Я сейчас выйду.
Это не поможет, Саш, не надо выходить, потому что кроме вас кто-то под вашим именем тоже вошел и занимается хулиганством.
Витя Семенович, а вы потом второго вы убьете, потому что вы хост.
Я не знаю, кто первый, кто второй.
Я сейчас, Иосиф Семенович, я сейчас выйду, а второго сейчас надо попросить аккуратно.
Да, а вы второго просто убьете и все, а потом Саша
Я
зайдет.
не могу убивать, значит, это Алик должен убить.
Иосиф Семенович, все, Александр Васильевич вышел.
Руководитель семинара может удалить любого пользователя из сессии.
Я руководитель на бумаге, но не в этом самом.
Нет, ну тот, кто ведет семинар.
Он уже удалился, этот второй Аксенов, так же,
Да.
как и предыдущий. Вот, но Я, к сожалению, не знаю, как убрать их рисунки.
Сейчас,
Ну
подожди,
да.
я
Попробуй
одну
сделать
секундочку. Я...
unshare и share again. Пусть Валентин
А,
попробует unshare и затем share again.
Значит,
что?
Валь,
Ну,
нужно,
закончить share screen и опять потом
да,
войдет.
да, ну, значит, ты его unshare, а потом снова share.
Еще что тогда unshare? Извини.
Ну, ты сейчас разделяешь с нами экран, ты отключи этот режим, а потом снова...
Вот.
А теперь снова сделай это самое.
Share.
Твой файл и...
Сейчас найду такое.
Ага, вот. Отлично. Все. Временно...
Ну вот, да.
Ага.
Я боялся, что это я чего-то творю этим самым.
No, it was not you. It's, well... Okay.
Yeah, so this is the case that we discussed. It's affine transformations of the line. This is invariance. And this is our choice of, this is literacy parameter. So we take A to be equal to 0 and B equal, this is the second invariant, Q2 divided by U1 square. So it's easy to find this is three-set derivatives. And it says us that if you have equation of order 4, and it's written in invariance, and after factorization, after passing to quotient, you will get equations of order 2. And this is what I wanted to mention, that it's the more or less general phenomena. So if you have an equation of order k and your group has dimension L, then the quotient equations will be order k minus L. X. Кто-то неубиваемый.
Just a moment. The same. Ага. Ага. No, but no. Саш, вы здесь или это...
Похоже, опять пошел, потому что 36 участников опять, как было до удаления.
Семенович, мы ничего не делаем, мне опять выйти?
Ну вот, нет, ну теперь вы в одном экземпляре, ну непонятно, что это такое. В общем, здесь какой-то...
Нет, это был другой, они под разными именами входят.
Покажитесь, кто это делает. Так, ну давайте я попробую еще раз.
Угу.
And so the last example with the ordinary differential equations, it's projective group, SL2. So then just below the list of invariants, we have 1 0 order invariance, 1 third order, and 1 fourth order, and etc. So once more, if you take A to be equal U and B to be the second invariant, then you will see that if you take differential equation that project invariants, it should be at least order 4. Then after passing to quotient, you will get equation of the first order. So it's one that I wanted to show for this. Yeah, and this is just some comments about integrability, because what we know that if you have equation of order k, then there is this Lieb-Yankee theorem that says if you have solvable Lie algebra and dimension of this algebra equal also k, then this equation can be integrated by in quadratures. And what we learned in these examples, that if you have differential equations of order k, and if you have symmetry algebra, but dimension k minus 1, then the integrability become reduced to integrability of first order equation. And it's can be done step by step. So you can, if it's say solvable, the algebra you can take subalgebras, say dimension 1, dimension 2, dimension 3, and so on, and you will reformulate integration in terms of some integration of some number of equations of first order. Now, just one example about equations in dimension 2. I'm sorry, I was lazy, and so I took, oops. I took constant.
I noticed it was someone with name Kostya.
Yes, yes.
Да, Костя Душкин и что-то такое.
Но это другой Костя.
Такого
Да.
Костя я не вижу, у нас нету.
В общем, как-то это неприятно. Это первый раз такое.
Yeah, so if you take equations with a constant coefficient, so it means that they have this symmetry algebra dx dy. So this is invariance of this. It can be different choices of this A and B's parameters. So I want to talk about the hyperbolic case. So I will take A1 and A2. It's now dimension 2, so it should be 2 A's. So it should be this first derivative U1 0 and U0 1. And B2 also 2, but I will denote 1B in this U0 0 simply by B as a second by C, because in other case it will be big mess in formulas. So B2 and B squared will be just either the same or different. So it's easy to find this is preset derivatives. So delta here is just a Hessian, so this is expressions for them. And you can easily find a syzygy between them. It's without any equation, just simple syzygy between them. This is a formula for this syzygy. Sorry.
Well, it will not help because he will do it again, or she.
Yeah, and so this is the syzygies for this case, and you can use this equation just to get quotients of equations of this form. So if you take equation of this form, U11, so the equations that you will get as a quotient equation, you should in this formula instead of this small c to put this capital C. And this will be just equation for the quotient equation. So two examples I will show. The first is equations U11 equals 0. And this equation is self-dual in this sense. So if you take quotient, you will get the same equation.
Yeah.
And the second, if you take, say, this equation, then the quotient will be just look like this. Okay. I am sorry for these extra pictures, but that's also what I wanted to tell you. Thank you.
Okay, thank you very much. Questions, remarks?
So on this example, can you maybe tell briefly how to go back? So you get quotient equation, how you actually can go back to solution of original equation?
So you should take this solution of you should take solution of the quotient equation and add to your original equation as a differential constraint. Because quotient equation is give a relation between differential invariants. So this is some function on Z. So you should take this and put it to your equation, and then you will get new differential equation. But what is important that equation you will get a finite type equation. So it means that Cartan on this finite, this equation give you just completely integrable distribution. And the group G will be just symmetry group of this distribution. So if G say solvable, then you have only quadratures to finish integration.
So like usually the equations are like, well, we just look for local solutions, right? For those equations.
What do you
even
mean
though
local?
all these quotients are global constructions. If you have for your quotient equation like local solution, can you get any kind of semi-globality for when you return to origin?
No. Quotient equation is a local notion. It's a local chat on this tower of projective.
No, you said differential. Differential is actually a global object, right? So when you embed it into jet space, yes, it's kind of local embedding, but in principle.
No, but when I said the quotient equation, every time I mean real equation, the chat on this is differential.
Yeah, of course, it's only local picture, and the global quotient is glued of these parts.
Yeah. Okay, but okay. So, but my question is anyway. So it will be different. So you take solution of quotient equation. Okay. So
Yeah.
usually you can guarantee only local. Now you return. That's basically equivalent to additional constraint, but and so it's finite type equation, kind of integrable distribution you integrated. Can you get any kind of global behavior? So is it possible here that you get
what do you mean global?
variation with dense fiber with the dense fiber?
Wait a second. What do you mean global? You have equation of the quotient. Now you take pre-image in your equation. So this projection of your equation of the quotient. You take pre-image of this. This will be just something that G invariant and Cartan distribution of this will be just completely integrable. This picture that you will get. What do you mean global now?
Well, actually, our basis is global manifold, right? And actually, there's the action of group has to be transitive there. So there's actually global picture somewhere here.
Yes, and so what?
So,
no, when I said equation, I mean submanifold in jets.
Like in your example, for example, one of the example was just translations, del x or del x1,
Yeah.
del x2, right? So basically, you completely quotient the base. What remains is just fiber, which is algebraic. So presumably, all constructions can be global because everything is algebraic. So when you return, so my question is it possible? So when we return, we get actually global solutions, not local solutions, but global solutions.
So you should take your equation. It doesn't matter, global this equation or local. Write this equation, and after this, take the solution of quotient, write as a relation between differential invariants, and add it to your equation. And then it's, yeah, certainly it's global. So yeah, I didn't fix X or something like this. So it's just, it's for all X's and for all these uses. But are you possible to solve this globally, locally? It's very difficult to say because it's, it's integration of completely integrable distribution, but I'm not sure that it can be done easily.
Well, but it seems to be local because you take a neighborhood of a point where differentials of your invariants are independent. And,
it will be global in base. This will be global in base because the assumption was that the group is transitive on base.
It's global in base, and
in the base it's global.
Let me show you. Say when you take, for example, this case, when you take this is invariance, then when you write this derivatives, you will see that you will divide it by this delta by Hessian. Yes. And so this is conditions when it's their coordinates or not coordinates. If delta is not equal 0, then it's okay. If delta equals 0, it doesn't work. And so, and you see, you have this your equation invariant, but you see x absent in this equation because GDEq and dy are the symmetries. So you take this equation, and this is CZG. So you just add the C to this, and you will get new equation. And this is equation now, it only intercedes derivatives. So when you solve this, you will find this b. But it will be just function of this is u1, 0, u0, u0, 1. And we should add this relation to
okay, yeah.
You should take this as u1 equals this b because b, this is really where it is. No, c equals u11 and b, this is, yeah, it's u0, u0. So you should take a solution of this equation, and this just will be relation between all this u and derivatives, and add to this u equation. So you will get one more equation, and yeah, it's certainly it will be just involve what it will be. Our b, it's u0, 0, and this is these two invariants. So it will be some relation of the first order. So if you add to your equation, you will get integrable situation and finite type situation, and the solutions of this will be solutions that will be corresponds to solution of this quotient equation. Really, this is answering the second question on the more simple question. So if you have this equation like this u11 equals the c blah blah, and I want to integrate this equation by adding one equation more. So this equation has just characteristic manifold with just 2 points. So if you add one equation more, you will kill these two characteristics. So you'll get finite type equation. The only problem will be just is it integrable or not integrable. And so you should add this equation, write Cartan distribution, and check it, is it integrable, is it completely integrable or not. And it's as a rule, it will be not integrable. But if you take this is relation between invariants that we will get by solving for this equation, then it will be integrable. Now it's Rafael Vitola.
Now it's Rafael Vitola. Raf, stop it.
No, it changes all the time. It's not a person.
It's not nice. Okay, Borja, are you satisfied?
Yes.
More questions, more remarks?
May I ask just historical questions? You mentioned Arthur Tresse, that did I understand correctly that you said that he first called the Lie groups?
Yeah. And he did it in his thesis.
But I think that he was Tresse, not Tresse. He was French. We all called it...
No, not Tresse.
No, if French, then Tresse. But if he's like closer to German borders, then it could be that he's...
Yeah, it depends, of course. But, well, Col Normal and so on. But maybe, well, I doubt that in 19th century Germans studied at Col Normal. Well, there was war.
No, at that time it's very difficult to say. German and French, it was very easy to travel from one part to another part.
Not like now, because there was no COVID. Okay. Well, more remarks, more questions. Okay, Varia, thanks a lot. So we say goodbye. Well, something is to be done with this bloody spy who interferes with our seminar. So next time we shall listen to...
We need, yes, we need Secret Service for our seminar. Just
yes, something like that. Yes, yes. Well, I'll call to KGB later. Okay. Thanks a lot. See you next Wednesday. I think that the next talk will be also very interesting. Well, goodbye.
Goodbye. Yeah.
Okay. See you
Bye.
next Wednesday.
Thank you.